forward with that, and then going forward with that is, so what we've actually seen so far, where I'll focus mostly on work that I've done with the South Pole Telescope, and then following up with what CMB surveys will be able to see in the future and how we'll be able to expand this work. And so with that, I'll be talking more about CMB-S4. So let's kick it off with why we want to observe asteroids at millimeter wavelengths at all in the first place. All right, so let's start with some high-level motivation of why studying asteroids is important. So a quote that is potentially too long that's up there, just basically sizes, shapes, rotational, internal, and surface properties of asteroids are outcomes of collisional and dynamic evolution that has molded them since they formed. And understanding everything, how those processes they experience, how mechanisms change their properties, and how these factors in turn influence their evolution can serve as a tracer to tell us the story of the solar system. All that is to say that understanding asteroids and their properties is important to understanding our home and how it developed and how it formed. So I've convinced you that asteroids are important and cool. How do we actually observe asteroids now that we want to observe them? So I'm going to do this a little diagrammatically. So we have a little asteroid in the corner here that we are going to observe. Somebody that really wants to observe an asteroid might try to actively look at it. So we can send and receive signals by studying it with radar. So we actively send a signal at the asteroid. We observe the signal that gets reflected back, and looking at things like the echo signal and looking at things like Doppler shift, we can tell things about the size, shape, and spin of the asteroid. You can imagine that we're not the only things that are lighting up an asteroid. There are other things in our solar system, like the sun. So visible solar light will hit the asteroid and get reflected. And so we can look at that visible light, and that tells us similar things about the size, the albedo, how much of that light is reflected back towards us. And you can imagine also that if sunlight is hitting something, it's going to heat up, and hot things radiate energy. So thermal energy, thermal radiation, primarily this will peak in infrared wavelengths. We can also look at that, and that will tell us things about, again, size, albedo, how much of the sunlight is reflected versus absorbed, so how hot it gets, things like that. But so thermal radiation, although it peaks in infrared, is not only at infrared wavelengths. It happens at a lot of other wavelengths, including longer wavelengths like millimeter, centimeter, and longer. It's just that it's a lot weaker at these wavelengths. And something that's interesting about these longer wavelengths in particular is that surfaces are more transparent to longer wavelengths. So thinking about, like, the sunlight doesn't necessarily come through a wall, but I can turn on a radio in here and we still see it. So if you look at some of these longer wavelengths coming from asteroids, you're actually peering into the surface of the asteroid because the top layers are slightly more transparent to these wavelengths. So if we want to look at millimeter and centimeter wavelengths, what can we figure out from doing that? So these long wavelength thermal radiation originates below the surface of the asteroid, just a little bit in. Something that's interesting about this is that historical observations at these wavelengths have found that objects are actually a lot dimmer than one might expect them to be. So this is a plot of the asteroid 4 Vesta. And so the y-axis is if you take what is the measured brightness that we're observing the asteroid at, and you divide it by what a model might suggest, and you plot it versus wavelength. So at some of these shorter wavelengths, like infrared, it's about as bright as you might expect it to be. So if you divide measured by model, it's around 1. But once you move to slightly longer, like a millimeter and centimeter, except for like this one weird data point, it's a lot less bright. So about 60% as bright as you might expect it to be. And so that's pretty interesting. And this drop off from being as bright as you expect it to be to less bright is not well understood. And since these wavelengths are emission is originating below the surface, studying this drop off tells us about the surface properties of the asteroid. So what it tells us, you could try to imagine what might cause these dimmer observations at long wavelengths. So you might imagine that the outer surface is hot because that's where the sunlight is, but as you get in a little bit more, it's slightly cooler, and so it's not going to be as bright. Or you might imagine something like it's just as hot, but as this radiation is trying to leave and escape the surface scatters the light and you don't see as much of it. So you can tell some things kind of like that about the surface of the asteroid. And given a shape model of the asteroid, so just one of my favorite asteroids, for instance, you can try to model and quantify these effects. So you can imagine shining a flashlight at this to picture it as the sun. Think about how it turns, think about how it heats up, and model how that heat distributes so that you can try to see if playing with some of these properties, like how much scattering happens or how cool it gets, how much heat is being conducted, you can mimic the same types of effects. So, all right, why observe asteroids at millimeter wavelengths? Is because you can learn interesting facts about the surface properties of the asteroids that you can't necessarily figure out about studying at other wavelengths. That leads us to why do we want to use CMB, cosmic microwave background surveys, to do that? So these are cosmological surveys. These are not meant to study asteroids. Why would we even bother doing this? So usually when people want to look at an asteroid, they look at the asteroid, they do a targeted observation and they study it. So for instance, of some millimeter observations, the European Space Agency had a spacecraft called Rosetta that included some millimeter detectors on it, and it did flybys of 2 different asteroids. Or you might consider some ground-based telescopes as well. So ALMA, which is an interferometer, took short duration but really high sensitivity measurements of some asteroids as well. And so it's actually able to observe the asteroids from Earth. And this is a GIF of Juno spinning from their data. But you could imagine that launching a spacecraft takes a lot of money. Building a spacecraft takes a lot of money. Taking time that on a telescope that you could be using to study something else takes a lot of time and money. And so this isn't necessarily always the best solution. And that's where surveys come into play. These are repeated observations of the same region of the sky. So you asteroid folk people in the crowd might know about WISE and NEOWISE. And so this was an instrument that took all sky infrared observations of the sky, and it was specifically designed to try to see asteroids. So if you're taking repeated observations of the same region of the sky, you can see objects that are moving through those observations. It's in one place in one observation. When you take a photo again at another time, it's at another place. And so it's estimated that it either already has or will see hundreds of thousands of asteroids. And this is identifying new asteroids, seeing these things move and identifying them. Some of you cosmologists in the background might be more familiar with the Dark Energy Survey. And so this took observations at UV, visible, and IR. And the main purpose was for cosmological purposes. But it can see asteroids that are moving through the field. And so if you say, okay, what are these moving objects? And you look for these moving objects and you try to fit orbits to them, you can identify new objects that are going through. So this is a Hubble image of a huge comet that was found by DES, just as an example. And so what's great about this is that it's a very low opportunity cost. The data already exists. We don't have to spend time and money to go observe these asteroids at millimeter wavelengths. And that's what's great about CMB experiments. We are taking these observations already at millimeter wavelengths, which is a useful wavelength to be studying asteroids. And so the data already exists. We don't have to be spending time and money to do it. And so what do CMB observations look like? So this is one observation is just one snapshot of the sky in millimeter. And as you might imagine, it hopefully contains the CMB. So this is an image of what a raw observation, a small cutout, might actually look like. And it looks pretty noisy to my eye. So it's not just the CMB signal, there's a lot of other stuff. There's a lot of noise, although you might not necessarily be able to point them out by eye. There are static point sources like stars in here. There's transient objects, things going boom, stellar flares, AGN, stuff like that. And then there's moving objects, things like planets and asteroids. And so all of these things aren't necessarily bright enough to see in these single observations like they are in some of these other surveys. So to use CMB observations, we need a more novel approach to actually make out the asteroids. So we can figure out what those static sources are in the sky by averaging all these raw observations. So if you take all these observations and you just average them on top of each other, you start seeing more more of this structure. So you can see some of this this waviness in the background. That might be the CMB. You can see some of these. Point sources here, and so you can figure out what's not going boom, what's not moving around. And so if you take these raw sources and you subtract off the average that we just figured out, all that should be left is everything else in the map. So you'll have noise, you'll have things going boom, and you'll have things moving around. And so while this by eye might look pretty comparable to the raw image, you know that it doesn't contain the static stuff that might be confusing. If we then take these differenced maps that should only have noise and transient and moving sources and pick an asteroid, any asteroid, and average them centered on where you know the asteroid should be, you can make out an asteroid. And so you can see it pops out in the center of this observation. We can do a little better than that. If we know properties about our noise and we know properties about our instrument, we know what our beams looks like, we can filter these observations to maximize signal to noise for point sources. So this is an asteroid. This is typically what you might expect some of these CMB observations to look like. You can see this in real time for an asteroid that actually is bright enough to make out an individual observations. So this is Desiderata. These left plots are its trajectory passing through a field. So this blue is the region of the sky that we're taking observations of. It's tracing out this loop. These center plots are individual observations. And then on the right is just averaging down as it's spending time. So we can take a minute to watch it go through. I'm actually going to, if you look at what it looks like now after it's averaged, I'm going to restart the slide so you can see it averaging down again. Goes down. And so we can make high sensitivity measurements of asteroids by doing this averaging technique. All right, so why do we want to use CMB surveys? Is because it's basically free data with low opportunity costs. The data is there. All it takes is somebody to go and look at it. Okay, so we are able to see these asteroids. So what actually has been shown to be seen so far? And so for this, I'll mostly focus on work I've done for the South Pole Telescope. So the South Pole Telescope, SPT, is an aptly named telescope at the South Pole. It's a 10-meter telescope. It observes at millimeter and sub-millimeter wavelengths. So right kind of in this boundary between where things are as bright as we expect them to be to where they go dimmer. SPT has observed with 3 different cameras. So this is a map of the sky. These colored boxes here and here are the observation fields that SPT has observed with those cameras. And so typically we like to make really deep maps of the CMB. And so we're looking at places where we can avoid really strong galactic foregrounds. So the background is a map from Planck that shows dust in the galaxy. And so this basically follows the galactic plane. And so you notice our fields are mostly in all the areas where that is not bright. Unfortunately for studying asteroids, that means that we won't see as many of them. So most asteroids have low inclination. They're all within the ecliptic plane. And so the ecliptic plane is plotted here in this dotted line. Our telescope is at the South Pole, so we're mostly looking at the southern sky. We can't see too far near declination 0. And so unfortunately, where the ecliptic goes furthest south also intersects with the galactic plane, which again, sad. But initially, what we've done is we're looking at these two bolded orange regions. So the subfields that get closest to the ecliptic plane, hopefully to see the most asteroids that we can make out. So these are plots of some of the asteroids that pass through those fields. So what you're looking at here, y-axis is model flux, so how bright we expect them to be. And x-axis is how many observations we are taking of these asteroids. So left panel is for one of those fields, right panel is for another one of those fields. And you imagine that to better see something, we want it to be bright and we want to see it for a long time so that we can average down noise. So most of the interesting objects are going to be in the top right of these plots. I'm going to be showing a couple of plots like this. So I'll hang on these plots for a moment just to make sure everybody has a good lay of the land. But so each different dot is a different asteroid. And I've traced out lines of different constant signal to noise. And so what you see in these two fields is that there's 3 asteroids in particular that should hopefully be pretty bright, and we should hopefully be able to make out to about 10 to 14 or so signal to noise. So what these 3 asteroids look like, these are plots of their trajectory. So declination on the y-axis, RA on the x-axis, top panel is for one of those fields, bottom panel is for one of those other fields. The color in this plot is actually the date that we're observing. And so each of these 3 asteroids we're basically observing for about a month each. Their trajectories are plotted on these dashed and dotted lines that go through the field. And so although they pass through the field at other points in time, we're not always looking at this field. Sometimes we're on, sometimes we're off. And so unfortunately, we were looking at both of these fields for only about a month each. But what you see is they're tracing out these loops. That's just parallactic motion, but it kind of helps because it helps put these objects back in our field for a little bit longer. And we mostly, that helps, that especially since our fields are so far south, it helps bump some of these low inclination asteroids into our fields. But to get a general sense, for some of these fields, we're only observing for about a month, maybe more, depending on the asteroid, maybe less if it's only clipping through for a little bit. And so these 3 asteroids are plotted on the right. So right panels are at 1 wavelength, left panels are at a 2nd wavelength. Top panel is 1 asteroid, Bamberga. The middle panel is another one, Egeria, and the bottom one is another one, Calliope. And so what you're able to see is at 2 millimeters, they're basically all bright enough to observe. You can see a bright point right at the center of our averaging. And what you're seeing at the slightly longer wavelength at 3.2 millimeters, they're not necessarily bright enough to see. So you can make out this asteroid. You know it's there because we're observing it at 1 asteroid. So it should be there. They're not necessarily bright enough to see. And so these asteroids are dimmer at this longer wavelength, and we can actually quantify how much dimmer by fitting models to them. So SPT has observed these 3 asteroids, and we've seen how dim they are. What can we actually learn about these asteroids? What do we take away from them? So 2 of those asteroids, Bamberga and Egeria, their measurements actually roughly agree with the model. They're around 1 on that plot that I showed before. So you can't actually tell too much just from these measurements alone, but this is still a useful constraint if somebody else takes measurements at a longer wavelength and goes back to look at that plot of how bright is it versus how bright we expect it to be. This is still a useful constraint to say at these wavelengths, it's what we expect. The story is a little bit more interesting for the 3rd asteroid. So this is an M-type asteroid. So its surface consists mostly of silicates and iron. So it's a little more metal rich than those other 2 asteroids. And so it's about 64% as bright as we expect it to be at 2 millimeters. And as you get a little bit longer, a little more into the surface, we can constrain it to being less than 46% as bright. How much less? Not sure. And so it definitely drops off and gets a lot dimmer than we expect it to be. And with some modeling, comparing it to some other asteroids, we expect that this is potentially due to a highly scattering surface. And so this can be used to talk about the size and shape of particles on the surface of the asteroid. So SPT didn't observe only these 2 fields. We expect that we'll observe about 34 asteroids over the life of the telescope. And so this is the same type of plot as before, where you have the flux, how bright it is on the y-axis, how long we're observing on the x-axis, and the color scale is our signal to noise of the asteroids. And so it's interesting to note out of these, I know there's a lot of asteroids that are listed here, but so there are some frequent visitors, things like Euphrosyne shows up here, 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 here. Some asteroids keep visiting our fields. There's some other cool asteroids in here too. So in particular, Patroclus here, NASA's going to be sending a mission to. So there's some cool, pretty relevant asteroids that we'll be able to observe. All right, so what's been seen so far? We've seen about 3. We've published results, detailed results on those 3 asteroids. Bump it up by an order of magnitude. We're hoping to see about 30 over the life of the instrument. But what will other CMB surveys be able to see in the future? We're basically going to be bumping this up by another order of magnitude. So CMB-S4 is a next generation CMB experiment, similar to SPT in the sense that it's trying to characterize the cosmic microwave background. It is observing at a lot more frequencies though. So SPT currently is observing at 3 frequencies. CMB-S4 is planning to observe at 8 frequencies that span a pretty broad range from millimeter to centimeter. And its survey is planning to basically cover 2 different fields for about a decade of observations. So these 2 fields, there's one called the deep survey. That's a pretty small area where they're trying to get really deep, really low noise, only about 3% of the sky. And the position on the sky roughly mimics the SPT fields. So I'm not going to spend as much time on this because results are going to basically mimic what I've shown for SPT. But where it gets a little more interesting is there's also what they call a wide survey that covers a really large area of the sky, about 70% of the sky. And it includes the entire ecliptic plane. So effectively every asteroid. Pick your favorite asteroid. It's probably going to be seen at some point by CMB-S4. And that wide survey is going to take about 1 observation a day. So it's also going to be sampled a lot less frequently than South Pole Telescope or the deep survey.
Yeah, well, does that mean all 70% are seen once a day, or just there are some fields inside the wide survey? Is every point visited once a day? Or?
My current understanding is that the entire 70% of the sky is going to be visited once a day. All right, so I'll talk about each of these surveys a little bit. So the deep survey, the small area, we'll start with first. So this is another one of those plots like I showed before, where you've got brightness on this axis and time and field for this axis. And these lines trace out constant signal to noise. This line here is signal to noise 1, and this is signal to noise 10. So basically, these are the asteroids that are going to be particularly interesting. So although there's thousands of objects present that will pass through this field at some point over the decade of observing, only about 18 or so are actually going to be seen pretty significantly. And so I'm going to show another plot that's basically zooming in on those asteroids. Same thing, brightness on the y-axis, time and field on the x-axis. This background rainbow color is the same thing, signal to noise. We got lines of 10, 20, 50, 100. Each point is an asteroid. The color of the dots, though, corresponds to how many of those 8 frequency bands we're going to be observing with. So like with the SPT observations, we saw, we were observing these asteroids at 2 frequencies. This is asking about how many of those frequency bands out of these 8 for CMB-S4 do we expect the signal to noise to be greater than 10? And so most of these objects you see are pink. They're being seen by about 4 frequencies. So already this is, even though there's only about 18 objects compared to about the 30 or so that have been seen by SPT, this is already an improvement in that we're going to be making significant measurements at more wavelengths. So that's mostly what I'm going to say about the deep survey, the small area of the sky. There are some interesting things though. So for instance, this object is a near Earth object that we'll be able to see pretty significantly. There's not too many near Earth objects that we're able to necessarily make out in some of these surveys. So moving on to the wide survey, this is a plot in galactic coordinates of the wide survey. So this bright background is the galaxy, and this black line is the ecliptic plane. And so you can see that this survey is going to cover the entire ecliptic plane plus more. So pick your favorite asteroid. CMB-S4 is probably going to see it. The question is, are these asteroids bright enough that we're actually going to get anything useful out of it? So we can show the same plot, and there are many, many thousands of asteroids that pass through these fields. So we got flux and time and field. This line here is signal to noise 10. And so there's about 3,000 objects that are at least signal to noise 1 that are going to be bright enough to probably be able to be seen somewhat. And there are about 600 or so compared to, say, the 30 that SPT is expected to see, the 18 that the deep survey is expected to see, that we'll be able to see pretty significantly a signal to noise greater than 10. So just like previous slide, I'm going to zoom in on these brighter asteroids. So we've got signal to noise 10 down here. Background rainbow color scale is signal to noise. All the way up to, this is Ceres, it's going to be signal to noise about 2,000. And so there are 611 objects plotted here. Same thing, the color of the dots correspond to how many frequencies we're observing them at. Most of them are going to be seen by at least 4 frequencies. Some of them, like these very brightest ones, up to about 6. But even if we aren't necessarily seeing them at all 8 frequencies, it's still a useful constraint because we know that the asteroid is there, so we can still look at how bright we're seeing them and the other ones where they're not necessarily as significant. But yeah, basically an order of magnitude better than we are currently doing with the South Pole Telescope. Question from Srini?
Yeah, so does this also take the beams into account? For example, the 30 gigahertz beam should be around like 8 arc minutes, right, for CMB-S4?
So I didn't necessarily take the beams into account.
Okay.
What I'm drawing from how I'm coming up with these plots are looking at the projected noise per day and how often they're being observed. So if that takes into account beam size, then yes, but otherwise I'm not necessarily doing anything.
Yeah, I think the nice, I think the beam is deconvolved in those nice curves. So I think you'll lose some signal to noise when you convolve your map with the beam.
Okay.
These are like pretty big beams, so the sensitivity should drop.
Okay.
Yeah.
Pretty big. Sorry. Pretty big means what exactly?
Oh, poor resolution, like 8 arc minutes.
8 arc minutes. So I don't.
Yeah, compared to around 1.4 arc minutes at 150 gigahertz.
Okay, well, thanks. That's very interesting. We can discuss this stuff later, I guess.
Right.
Yeah.
And
yeah, it looks like on this plot, the number of frequencies is kind of correlated with the predicted model flux.
Mm-hmm.
Why is that? I would have expected it to just be about the. Oh, it's the 10 sigma cut. Oh,
yeah. So this is the 10 sigma cut. I'm plotting all of these for their signal to noise at 145 gigahertz, 2 millimeters, which is where we're most significant, just for where these asteroids are peaking in their brightness, and given the expected noise at all of these different frequencies. So they're most likely to be brightest at this, and just as they get brighter, they're going to be brighter in all bands. So as you move up in brightness, they'll be seen in more bands.
And so the ones that buck that trend are the ones like those 2 green points that are pretty high up.
I mean, they still buck the trends. So these ones down here, that might be a little bit of the color scale. Yeah, this is the like kind of a teal 1, and these are 5. Yeah.
Well, I think you said it before, but I just want to make sure. This is, so the x-axis is time being observed, not just the time that it's in the field.
Yes. Mm-hmm. Yeah, and so the cuts for signal to noise are based on expected noise per day. All right. So answering these questions from the overview, some main takeaways from this talk. So why do we want to observe asteroids at millimeter wavelengths? It tells us about the surface composition of the asteroids, and it gives us constraints that we can't get by observing asteroids at other wavelengths. Why do we want to use CMB surveys to do this? Is because it's basically free data. There's no opportunity cost to measure. We're already making the observations. All it takes is somebody to write up some code and hit play on a pipeline and get results. So what's been seen so far, 3 main belt asteroids, details of those have been published by South Pole Telescope. And what will CMB surveys likely see in the future? So approximately dozens or so asteroids with the South Pole Telescope and CMB-S4 Deep Survey, and approximately hundreds or so with the CMB-S4 Wide Survey. So thank you, and we can open up to more questions.
Thanks. So time for questions. I think Pascal had one. Do you want to unmute?
Yeah, I just posted a question in chat. So I was wondering, using CMB for getting details about these asteroids, it won't work for new asteroids, right? It will only work if we already know the asteroid and know their trajectories. Then only we can stack the CMB images appropriately and make out the asteroid from that.
I mean, so not necessarily. So for instance,
if it's bright enough, then yes.
Yeah, some of them are bright enough, like this one, where it's maybe a little bit easier and you can try to look for bright ones. But for the most case, ones that are bright enough to be seen in individual observations probably will be found by other surveys like WISE or NEOWISE. We are just much less equipped to do that. So we're looking at thermal emission, looking at the thermal emission in IR. It's just a lot better for doing this. But also, even if the asteroids are still too dim to be seen in single observations, you can still make them out. It's just instead of looking for moving objects and then trying to fit trajectories to them, you kind of go backwards from that, where you vary parameter space to come up with different trajectories. And then you take cutouts and stack on those trajectories and see if the outcome looks like. Yeah.
Oh, that's really interesting.
Yeah. So for instance, all of these 3 published asteroids are not bright enough to be seen in individual sources. So theoretically, if you came up with some trajectory that looked like their trajectory, you'd be able to recreate this.
They're not bright enough in millimeter wavelengths.
Yes.
But in visible, you can't see them.
Yes, you can see them in visible or in IR. Yeah. So these were all of the asteroids that I plotted on like plots like this are known asteroids that have been seen before.
Are these observations significantly affected by like LEO satellites that are like kind of polluting the sky? Like, is this going to be a problem in the future, or?
Yeah, so that's actually something that that we spend a bit of time on is trying to identify and take out satellites that go through the sky, and things like Starlink are going to mess with our observations. But one thing at least is it's kind of easier to differentiate satellites versus like main belt asteroids, for instance, because the satellites are moving so fast that when we take a picture, they look like a streak going through the data versus these look like just a point.
Do you have an estimate on maybe like the lowest, either absolute magnitude or diameter of the objects that are visible?
So depends a lot on how far away the asteroid is to. So there's a play of most of the main belt asteroids that we're able to see are larger ones. Like all of these 3 are about 100 kilometers or greater. You can still see near Earth asteroids though too. So for instance, that one near Earth asteroid I think is 4 kilometers across, and it's just a lot closer, so you can still see it. So yeah, it depends on, yeah, but there's some benchmarks to kind of rough estimate. Yeah.
So, like, you can say that some asteroids are 40%, so less visible than you expect them to be. Would you characterize how many asteroids
approximately know, considering that you can't like observe some at all?
Mhm.
Like, can you put like a number on like, I was wondering if you could put a number on how many asteroids there are total, for example.
Oh,
Yeah, is this like,
there are hundreds of thousands of known
Yeah.
asteroids. Is that your?
I guess like, because you've shown that there are some that you can't see, that have a different, sorry, their expected brightness is much
Mhm.
higher than you saw, right?
Yes.
Yeah, so
Yes.
given that you have some instruments which can only see a certain like brightness of asteroid.
Yeah.
There are some asteroids which,
So you're saying kind of the ways that we normally find asteroids, maybe they're missing other ones.
Yeah.
So the asteroids being dimmer than expected is mostly seen at longer wavelengths. So when you're looking at the cooler, yeah. So for things like WISE or NEOWISE that are using thermal emission to do this, you like that's near the peak brightness, or they almost all fit to some degree, plus or minus however much in what might be predicted by the model. And then also there are also like optical surveys that you don't necessarily expect them to be that much dimmer unless for some reason they absorb everything and they don't really reflect any light. Mhm.
Yeah, so this question's inspired by some of the questions that were just asked. Is there actual like hope for discovery of new asteroids with CMB-S4? Or is Bear Rubin and all these other ones going to find them all? And, you know, we talked about how you could do it, but
yeah,
is there going to be a parameter space where SPT is, where CMB-S4 is going to?
I don't know, that's a good question. I think in part it depends on whether or not there's interest in having somebody go and do that, just because to trace out all of those different trajectories takes a lot of computational time too. So, I mean, sure, there's probably a potential that you might be able to find something, but I think there's a playoff of whether or not it's necessarily worth devoting that much resource to doing so. Yeah, but I haven't thought necessarily too much about the like, what is the projection of finding something?
Mm-hmm.
Yeah.
Okay, thanks. And I had a second question, which is for this. So one of the arguments for why these observed fluxes don't match the model is scattering. Yeah, I couldn't quite intuit how that works, because you have some stuff that scatters this thermal light, but it still gets emitted, right? Is it getting reprocessed to different wavelengths? Or?
So it's yeah, so it's like things that are coming directly like radially out of the asteroid will get absorbed by those particles and then re-emitted or like scattered, and they're not necessarily coming out radially anymore. And they go in different directions. Or sometimes you get things too, there's an effect called like beaming, where it actually makes the asteroid look brighter, where if you have like a crater and you have some emission trying to come out of the crater and it gets sent to the other side of the crater, and then these photons just bounce around the crater for a while and it just heats up more than it should and then goes out, it actually looks slightly hotter than it might.
Okay. So basically you have some,
yeah, you just have
isotropic emission.
Yeah.
And then if you're looking, okay, but the spinning doesn't average that down, or
the spinning of the asteroid?
Yeah.
Not necessarily, no. Yeah, so you have so the way I think about it, you have photons trying to come from subsurface. If you have particles of a certain size above it, they basically will get reabsorbed by that. And so it's light that's trying to get out that ends up just making the outer surface hotter than it should be. And that light, so then that comes out again, but then you're seeing that as what might be, it's just the outside temperature. So that's another reason that like if you observe the outside temperature, that fits with the model. And then if you're looking, you're seeing less emission than you should be, because some of that emission is getting absorbed and being confused with absorbed solar light or something like that.
Right. Do we have any more questions from folks online? You can just unmute if you want. If we do not, then let's thank our speaker again. I will stop the recording. Thank you so much. And hopefully we see each other again in the next CAT seminar.